In this lecture, we start looking at finite volume methods and get into some of the issues with developing numerical methods that will work well for hyperbolic PDEs. So I'll quickly go through some of the main ideas here. We'll mostly be looking at finite volume methods, but there are many other sorts of numerical methods for solving differential equations, and one that you may be more familiar with is a finite difference method. The standard idea in a finite difference method is that if we're approximating a function q of xt, we think of q sub I super n, for example, as representing an approximation to the solution at a discrete grid point x sub I at time t sub n. And we put down a grid, as shown down here at the bottom, in the xt plane. So t is going upward, x horizontally. The grid points would be where the grid lines cross. And then the idea is that we approximate the derivatives in the differential equation by finite differences. So for example, if we just look at the advection equation, in the case u is positive, for example, then a standard method is called the first order Upwind method. We'll see later why it's called first order accurate. But it's based on approximating the time derivative qt by a difference in time, qi at time n plus 1 minus qi at time n divided by delta t, and the derivative qx by a finite difference in the x direction. And if we're assuming that u is positive, then the upwind direction would be looking to the left. The flow is going from left to right. The characteristics are moving from left to right in as the flow goes forward. And so this form of the upwind method is, for this case, u greater than 0. And we approximate the solution qin plus 1, which would be this point, in terms of a finite difference in x that uses the same point and one point to the left, so that we're looking in the direction that information should be flowing from. And as we'll see when we look at stability, that's a necessary condition in order for this method to be stable, that we're using data that is coming from the right direction and where we can approximate the solution. We can hope to approximate the solution based on the data that we're using at the previous time step. And so replacing those approximations, we end up with this form of the upwind method for advection, which is sort of a standard method for solving the advection equation, the upwind method. We'll see that we can derive exactly the same form from a sort of finite volume framework, but I wanted to remind you first what the finite difference approximation is. And the sort of natural thing about finite differences is that if we assume q is a smooth function, then we can use Taylor series expansions to figure out how accurate these approximations to the derivatives are. And if things are nice and smooth, you can expect that this will converge to the right solution as you refine the grid under certain stability conditions that we'll look at later. But the problem with finite difference approximations is that they really do sort of inherently assume the smoothness. For approximating things with pointwise values, and we're using finite difference approximations to derivatives. But for hyperbolic problems, we'll often be interested in problems where there are discontinuity shock waves in the solution. And so we can't really assume smoothness. And so a more natural way to define things for hyperbolic problems often is to use finite volume methods, where we look at qin not as being an approximation to a pointwise value, but rather an average of the value over a grid cell. So in one space dimension, our grid cell would just be an interval, say from xi minus a half to xi plus a half of length delta x, and the cell average would be this integral. And this is very natural because we've looked at deriving hyperbolic equations from this integral form of the conservation law, which, if we look at the interval corresponding to a single grid cell, it says that the time derivative of this integral over a grid cell can be written in terms of the difference between the fluxes at the left and the right edge of the grid cell. And if you manipulate this and assume things are smooth enough, you can derive this differential form of the partial differential equation. But numerically, we can work with this form and work with these cell averages and fluxes at the edges of the interface in a way that makes sense even when the solution is discontinuous. And we can build up methods that are more robust often than what you might get by trying to develop finite difference methods directly. So the idea, again, in the finite volume method is that we would integrate over a grid cell, look at the integral form of the conservation law, but now also integrate in time from time tn to tn plus 1. So I've just taken the top equation, integrated in time, so that says that, well, this isn't exactly the cell average. We have to divide by delta x, but it says that the integral of q at time tn plus 1 over a grid cell is equal to the integral at the previous time step plus the integral in time when we integrate in time from tn plus to tn plus 1, the integral in time of the flux at the left boundary minus the integral in time of the flux at the right boundary. And then we can make this look more like the finite difference method if we divide by delta x so that these become cell averages. And then the integrals in time we want to divide by delta t so that they look more like approximations, averages of the flux over the time step. We're integrating over a time step of length delta t, so we divide by delta t to get an average flux. And so I've introduced the delta t divided by delta t, and then if we define some numerical flux, fi minus a half n, that's some approximation to the integral of the true flux, then we end up with a numerical method that has this form, where the cell average at time n plus 1 is equal to the cell average at time n minus this delta t over delta x factor times the difference in some numerical approximation to the integral of the exact flux. If we use the exact integrals here, this would be an exact evolution equation for the cell average, but numerically we approximate this flux by some numerical flux that's based on the cell averages on the two sides. So that's the basic idea of the finite volume method. So if we go back to the advection equation, we can write that as a finite volume method in this framework, where the flux now should be some approximation to the integral in time of the flux, which is just u times q for the advection equation. So it would be an approximation of the flux at the left edge would give us the fi minus a half, and we'd integrate from tn to tn plus 1 and divide by delta t. And if we're looking at grid cells like shown down here at the bottom, and we have an advection equation with a positive velocity again, so the characteristics are going this way, then if you think about it, at least if the time step isn't too large, the values, if we think of the initial data as sort of corresponding to these cell averages, then the flux across this interface is always equal to the value coming from the left. So the flux at the left edge of this grid cell is just u times the value qi minus 1 in this cell I minus 1 over here. And the flux at the right edge, fi plus a half, would be the flux u times the value of q in cell I, which is this cell here. So that gives us then the new cell average, qin plus 1 is the previous cell average, plus this delta t over delta x times the difference in fluxes. And if we rearrange that, we get exactly the same Upwind method that we derived from the finite difference formulation. It's just a different way of looking at it for the advection equation. So this is just writing that out again. The flux is well, in the case u positive that we were looking at, the flux at the left edge of the cell is u times q in cell I minus 1, the cell to the left. But if u were negative, so that the flow is going from right to left, then the flux at each interface would be the value from the cell on the right. And so in that case, at cell interface I minus a half, it would be the value qi in the cell on the right that would be determining the flux at the interface between cells I minus 1 and cell I. So the Upwind method, what we call the Upwind method, is actually, it has different form again if u is positive or negative, but it's always taking the difference in the upwind direction, or in terms of fluxes, looking at the fluxes of the interface that are determined by what's flowing in from the cell that's feeding information across that interface. So this gives us a method that's said to be in conservation form. So any method that sort of has this form here, where the new value qin plus 1 is the old value minus delta t over delta x times the difference of some numerical flux functions, however you define those fluxes, that's always said to be in conservation form, because if you take this and you multiply by delta x and you sum it up over all of the grid cells, so you sum up delta x times the qin plus 1, then you'll just get delta x times the sum of the qi's, and then you'll get delta x times the sum of all these differences. Well, when you sum all these differences in I, you get cancellation going on. The flux at each boundary contributes to one cell average with a plus sign and to the neighboring cell average with a minus sign. And so when you add them all up, they all cancel out, except for the fluxes at the two boundaries. If you were on a finite domain, it would be the flux at the left boundary, and the flux at the right boundary of the domain would be all that's left once you've summed things up. If you were doing a Cauchy problem, then, and you thought of a hypothetical infinite grid, then you'd have to assume that the value of q is sort of approaching some constant state as you go to infinity, and so the fluxes are approaching some constants at plus and minus infinity, and everything else in the interior would cancel out, and you'd just be left with the difference in fluxes between the plus infinity and minus infinity. And this is a sort of analog of the true conservation law for thinking of q as being some conserved quantity that says that the integral of q in time should be constant except for the fluxes at the boundaries of the domain, or the fluxes at plus and minus infinity for the Cauchy problem. So this delta x times the sum of q over I is just a numerical approximation to the total sum, because these qi's are cell averages. They're approximations to 1 over delta x times the integral over a single cell. And this conservation form turns out to be very important when we get to nonlinear problems and trying to compute shock waves properly. So we'll go into this in much more detail later, but just to give you a sort of preview of what's coming, if we look at Berger's equation, for example, which is the scalar nonlinear problem where the flux function is 1/2 u squared, then if you write this in quasi-linear form, 1/2 u squared is just, the x derivative of that is just u times ux. So the quasi-linear form actually looks like an advection equation, except the advection velocity is equal to the quantity that's being advected, conserved quantity. And for smooth solutions, these two equations are equivalent. They have the same sets of solutions. But once we start looking at discontinuities and shock waves, they're not equivalent, and it's very important, if you want to capture the shock wave properly and get it propagating at the right speed, it's very important to be calculating with a numerical method that's in conservation form. So for example, we could think of extending the Upwind method in a couple of different ways. One way would be if we know that u is positive, for example, so that information is flowing from left to right with this advection velocity u, then one way to extend the Upwind method would be to do a conservative method like this, where we're look at the flux, the 1/2 u squared, and if u is positive, then the flux at the left edge of the cell, well, the flux at the left edge of the cell would be the 1/2 ui minus 1, and the flux at the right edge of the cell would be 1/2 ui squared, and we'd end up with this flux difference. And so this is a method that's sort of an analog of the advection Upwind method, but using the flux function 1/2 u squared and the direction in which u is flowing. And so this is a conservative method, and using this method, you will actually calculate the right shock speed. It may be smeared out a bit, it might not be completely accurate, but at least the shock will be going at essentially the right speed. But another way you might think about doing this is to start with this quasi-linear form, the ut plus ux equals 0, and just do exactly what we did for the advection equation, with taking u times ui minus 1, only now the u out in front is no longer a constant, it's uin itself. So this is also, you could view as an Upwind discretization of the ut plus ux equals 0 equation in the case where u is positive. And for smooth solutions, these two methods are pretty comparable. But again, once you have a shock wave, they can give very different results. So just one example. This is an actual numerical calculation that we'll look at later of a shock wave where the correct solution is the discontinuous solid line here. If you solve it on some particular grid with the conservative method, you get a figure like the top. It's a little bit smeared out. There's a few cell averages that are not exactly at the upper or lower value, but it's at least representing a discontinuity in the right location. Whereas if we use this quasi-linear Upwind method, we get the solution at the bottom, where it looks sort of similar. If you didn't know what the exact solution was, you'd say, oh yeah, there's a shock there, but it would be at exactly or completely the wrong location relative to where it should be. And if you refine the grid so that it's sharpened up more, it would stay at the wrong position. So how can that be? Well, to just give you a hint of why you shouldn't expect necessarily to get the right answer here, if we look at this conservation law, Berger's equation in conservation form, you can take another equation, this one here, ut squared plus 2/3 u cubed sub x, and that's an equation that's in conservation form. You can think of q as being u squared in this case, and the flux f of q as being 2/3 q to the 3/2, which would then be u cubed. So that's a function or a differential equation in conservation form, but the conserved variable here is u squared rather than u. Okay, but both of these equations, if you write down the quasi-linear form, they're both identical. They're both this ut plus ux equals 0. So all three of these equations for smooth solutions can give the same solution. But when you have shock waves, or weak solutions, as we'll call them later, when you have a discontinuity and it's not strictly satisfying the differential equation, but instead some weak form based on intervals, then these equations do not have the same shock speeds. So we have two different conservation laws here, one for the conservation of u, one for the conservation of u squared. They both have the same quasi-linear form, but they have different shock speeds. And so if you're solving things based on the quasi-linear form, there's no guarantee that you'll get the shock speed corresponding to conservation of u, which is the one we want. You might get the shock speed corresponding to conservation of u squared or some other conservation law. There's infinitely many other conservation laws that have the same sort of quasi-linear form. So that's just kind of a hint of where we're going, but that shows the importance of using conservation form and why we care so much about keeping things in that form. Okay, well, I want to switch gears a little bit now and talk about a very general method called Godunov's method, which is a generalization of the Upwind method idea that's much more robust for systems of conservation laws than the sort of methods that you would get by doing finite difference approximations typically. So this was a big breakthrough in the 1950s, I think it was late 50s, when Sergei Godunov came up with this idea for solving conservation laws based on solutions of the Riemann problem. Prior to that, people were mostly using finite difference sort of problem approximations and having all sorts of problems with approximating strong shock waves, with getting highly oscillatory solutions and solutions where the shock waves weren't in the right location and people didn't understand it for quite some time. It took a while to sort all this out. But this idea of Godunov's method was kind of the key breakthrough in terms of developing better numerical methods. Like the Upwind method, it's only first order accurate, so it's not very accurate as you refine the grid for smooth solutions. But as we'll see, we can sort of use what are called high resolution versions of Godunov method that restore something at least closer to second order accuracy and are actually quite effective for computing. So the idea in Godunov's method is that, again, we'll look at this sort of finite volume representation where we have QIN is an approximation to a cell average over one grid cell at time n, and QIN plus 1 will be a representation of the cell average over the same grid cell at at the more advanced time. But now the idea is to look at this QIN as defining a function at time Tn that's piecewise constant. So it's got the value QIN everywhere in this cell, and it's got the value QI plus 1n everywhere in this cell, for example. And so then if we just evolve the PDE forwards in time with that piecewise constant initial data, then at the interface, where that jump is, we have exactly a Riemann problem in time. And so if we know how to solve the Riemann problem for our system of conservation laws, then we can compute the Riemann solution at this interface. And we can do the same thing at every interface. So we have a Riemann problem at the interface between each pair of grid cells, and at least for a short enough time, the solution of those Riemann problems don't interact because we have finite propagation speed given by the eigenvalues of the A matrix or the Jacobian matrix in the nonlinear case. And so as long as you take a small enough time step, you can actually piece together, in principle, the exact solution over this time step of length delta t. And then you could think about various ways in which you could use that sort of concatenation of Riemann solutions to determine the new cell averages at the end of the time step. So one natural way to think about it is that you simply take this exact solution that you've computed based on all the Riemann solutions, and you actually compute the cell average. In the figure shown here, this might be acoustics, for example, where there's two waves coming out of each Riemann problem, one moving to the left, one moving to the right. And so within each state, there would be actually three different values, piecewise constant states. And so the cell average you could get by averaging those three. At the end of this lecture, we'll look at exactly what that formula gives us for acoustics. So that's kind of the natural physical way of interpreting Godunov's method. But that's not necessarily the easiest way to implement it, because figuring out what that piecewise constant function is, especially when you have a system with more equations, and then actually computing that integral seems a bit messy. So there are other ways that are computationally more efficient. So a second way to do it is to use this idea of flux differencing that we've already seen, because when we solve these Riemann problems, one feature of the Riemann solution is that it's constant along rays coming out of the origin. And so in particular, it's constant, the Riemann problem that's defined at this interface is constant along the grid interface. So even though the solution has these jump discontinuities that are propagating, the value of Q is constant along that interface. And the value of Q is also constant along this interface in that Riemann problem. And so if we remember the previous formula that the new cell average is the old cell average as updated by integrals in time of the fluxes at the interface, that's relatively easy to compute because the flux at the interface is constant in time. And so if we just know what that value is coming out of the Riemann problem, we can actually use that as our numerical flux in this flux differencing scheme. So that's a very useful way to look at it in some contexts, and we'll look at some methods that are sort of developed directly on that idea. But there's also a third way of looking at it, which is kind of the way that I prefer to look at it and the way that's implemented in the Clawpack software. And that is to look at the Riemann problem as defining a set of waves that are propagating away from the interface, and each of those waves is entering one of the cells to the left or the right. And as it passes through the cell, it's changing the value of the cell average everywhere that it moves through the cell. And so we'll talk more about this notation later, but we can define this A script plus or minus delta Q is basically the sum of all of the waves that are going to either the right or the left for the plus or the minus, multiplied by the positive or negative part of the wave speed. So the positive part of S plus just means S if S is positive, or 0 if S is negative. So it's the maximum of S and 0, for example. And S minus is the minimum of S and 0. So it's S if S is negative, or 0 otherwise. And we'll see later where this comes from exactly. But the basic idea is that we take all the waves coming out of the Riemann problem, and we use each of those waves to update the cell average on the left or on the right, depending on which direction it's going in. And it turns out that's sort of very easy to automate from after you've computed the Riemann solution to use those waves to update the cell averages on either side. But if we step back a minute and look at the flux differencing formulation, so here again, we would be defining the new cell average based on the old cell average and the fluxes at the interface. And since the solution is constant along the interface, the flux along the interface can be determined directly from this value that I've called Q with this funny symbol here that's supposed to kind of make you think of a set of waves coming out of a Riemann problem. So you might pronounce this Q Riemann or something. So this is Q Riemann or intermediate Q or something between states Qi minus 1 and Qi. So if we have a cell Qi minus cell average Qi minus 1 at time n here and Qi at time n here, then the Riemann problem between the two has a constant value along this interface, and that constant value, which you can also think of this function Q tilde n as being the sort of the exact solution here. Q tilde n of xt is the exact solution of this concatenation of Riemann problems. Once we put them all together, that function is constant along this cell edge, and its constant value is the value of Q that comes out of this Riemann solution. It's sort of the value that lies along the line x over t equals 0 when if you solve a Riemann problem at x equals 0 and you have waves coming out, then x over t equals 0 corresponds to the interface here. And so if you can calculate from the Riemann solution that one value of Q right along the interface, then the integral in time of f evaluated at that value divided by delta t is exactly equal to that value because it's constant in time. So the numerical flux fi minus a half n would then just be f evaluated at that Q Riemann value that comes out of the Riemann problem between Qi minus 1 and Qi. So going back again to the advection equation where the flux is just uq, in this case, if we look at the Riemann solution, depends on whether u is positive or negative, but if we have u is positive, for example, then the Riemann solution has a single wave that's moving to the right. Say this is x over t equals u, would be the speed of the one characteristic coming out of the Riemann problem, in the case u positive. And the Riemann solution would have value ql everywhere to the left and qr everywhere to the right. And so the value along the center line here would be exactly the left state. And so if we use this at an interface between now cells Qi minus cell I minus 1 and cell I, so QL is Qi minus 1, QR is Qi, then that says that the flux along the interface is just U times Qi minus 1 in the case where U is positive. If, on the other hand, U is negative, then we have a single characteristic going to the left at speed x over t equals U, and in that case, the value along the interface here would be the value to the right, Qi, rather than the value to the left, Qi minus 1. So that using that flux function gives the Upwind method, which looks, again, slightly different depending on whether U is positive or negative. Okay, now another way to look at this that kind of leads more into this wave propagation form, or looking at how a wave affects the cell average. As I've said, we can think of Godunov's method as reconstructing this piecewise constant function q tilde of x at time tn, defined from the cell averages. So the qn tilde of xtn is identically equal to qin everywhere in cell c sub I. That's the one from xi minus half to xi plus half. So that defines a piecewise constant function. And then we can evolve the equation exactly forward in time to obtain the solution at time n plus 1. And then we can average that function over the grid cells at the final time to get our new cell averages. That's sort of the first interpretation I gave you of Godunov's method. Of course, in practice, we'll also look at sort of evolving the hyperbolic equation only approximately rather than exactly. When we start looking at nonlinear systems of equations, then in principle, you may be able to solve the Riemann problem, but to do so exactly at every interface between grid cells, every time step can be monumentally expensive. And so there are things called approximate Riemann solvers that are often used to do this evolution step more approximately. But this is sort of what I'll often call the REA algorithm for reconstruct, evolve, and average. And we'll look also at how to generalize this from a first order method to a second order method by introducing piecewise linear functions instead of piecewise constant functions in the first step. So this algorithm will be built on in various ways as we go forward. So again, if we look at advection, then the pictures here, there's one case for U positive, the other for U negative, but in each case, the bottom figure shows this piecewise constant function that's been defined based on the cell averages. The middle figure shows how that evolves. In the case of advection, it simply shifts to the right if U is positive, for example. And the top picture shows the solution at time tn plus 1, delta t later, where each one of these discontinuities has shifted to the right by a distance u times delta t, if u is the advection velocity. Or if u is negative, then each discontinuity shifts by u times delta t to the left rather than to the right. So another picture, this is a case where u is positive. We have some cell averages, the dots. We have a piecewise constant reconstruction after evolving it with a positive velocity over some short time step. U delta t has shifted this slightly into the next cell. And notice, by the way, here that I'm sort of assuming that u times delta t is less than or equal to delta x, the width of the cell, so that these shifts are staying within the neighboring cell, and that's going to be very important, and we'll look at stability conditions in the next lecture and see that that's a requirement for this method to be stable. So here's another picture just blowing up on a single cell. And now what I'd like to look at is sort of how is the cell average QIN modified as this wave goes in. So this dot right here is the cell average QIN at time n in this cell. And we've now approximated the solution by piecewise constants with that value everywhere in the cell. But after evolving the conservation law, this discontinuity here has shifted over by a distance u delta t. And so as it shifts over, this higher value, in this case qi minus 1n, has shifted into the cell a distance u delta t. So there's some jump in q that's shifted into the cell a distance u delta t. And so the product of those two, which is the numerator here, u delta t times the jump in q, is the area that's shown in blue up above. And that means that if we compute the new cell average, it's going to add that area to the integral, and then we're dividing by delta x when we compute the cell average. So the cell average is modified by this blue area divided by the length of the cell delta x when we calculate the cell average. Which means that the effect of this one wave moving into the cell is that our old cell average, QIN, has been modified by exactly that factor to get the new cell average, QIN plus 1 at the end of the time step. And this again is just the Upwind method we've seen several times now in the case U positive. A different way of viewing it in terms of the effect that this one wave has had on the cell average. And notice that this jump in Q is the sort of the magnitude of this wave that's moving into the cell, or in terms of the solution of the Riemann problem, Qi minus 1 is exactly the jump across the wave. Since it's advection scalar equation, the entire jump between Qi and Qi minus 1 is carried by this one wave, if we had a more complicated system of equations, acoustics or something else, then the jump between qi and qi minus 1 would be split up into eigenvectors for the waves, but here the entire jump is carried by this one wave, and this one wave updates a single cell, the one to the right, assuming u is positive. But we can generalize this quite nicely now to systems of equations and think about what's the effect of each wave on the cell averages. So this is just kind of rephrasing what we just saw, but writing it in terms of these W's, which are the notation I've been using for the waves coming out of a Riemann problem. Again, for advection, there's only one wave. W is the jump in Q across that one wave, and S here is the symbol I'll use for the speed, which for the advection equation, the only wave speed is the value u. That's the one eigenvalue in the one-by-one case. And so the Upwind method we've seen a couple of times, but here's a slightly different way of writing it in terms of that works now whether u is negative or positive. You can look at it as the positive part of u times the jump in q between qi and qi minus 1. So if u is positive, again, u plus is u if u is positive, or 0 if u is negative. So if u is positive, then this is u times the jump in q, just the standard Upwind method for u positive. If u is negative, on the other hand, this term drops out, and instead you have this term come into play, u minus, which is u if u is negative, and 0 if it's positive. You would get, in the case where u is negative, you would get u times the jump qi plus 1 minus qi. And so you can look at this as being the wave that corresponds to the jump between qi and qi minus 1 that's moving in from the left, but only if the wave speed is positive, and the wave from the right edge is moving in only if the wave speed is negative. And again, this can now be generalized to look at a set of waves and speeds that are given by eigenvectors and eigenvalues of the coefficient matrix for the linear system case. So here's just a schematic for a system with 3 equations, linear system, say, of 3 equations where there's 1 negative eigenvalue and 2 positive eigenvalues. So in general, we would take the jump between qi and qi minus 1 between this cell and its neighbor to the left, for example, and we would break up that jump as a linear combination of the 3 eigenvectors of the matrix A, if it's a 3 by 3 system, and that's what we would call the 3 waves, p going from 1 up to 3 in that case. And then the new cell average for this particular cell qi, the new cell average would be the old cell average down here as modified by each of these waves. And so, for example, this wave W2 I minus a half is moving to the right. If the second eigenvalue is positive, it's going to distance lambda 2 times delta t. And so its contribution to the cell average is lambda 2 times delta t times the jump across that wave, and then divided by delta x in order to influence the cell average. Similarly, for this W3 wave, that gives you lambda 3 times delta t times W3 divided by delta x is its contribution. And then if we look at the other wave that's coming into the cell, it's the one that has negative wave speed, lambda 1, and it's moving in a distance lambda 1 times delta t. It carries a jump W1 proportional to the eigenvector of A corresponding to lambda 1, and then we divide by delta x in order to get the influence on the cell average. So this, for a system of 3 equations with 2 positive and 1 negative eigenvalue, would be sort of the formula. But you can see, I think, how this would generalize to a general system of equations. And you can also look at it for a linear system in terms of a decomposition of the matrix A. So if we think of taking the matrix A, which we assume we can diagonalize with eigenvector matrix R, you can split up the matrix A into, or split up the matrix lambda, rather, the diagonal matrix, into lambda plus and lambda minus, where lambda plus corresponds to only the positive eigenvalues, putting 0 on the diagonal for any location where the eigenvalue is negative, and similarly lambda minus only has the negative eigenvalues or zeros on the diagonal. And the sum of the two is lambda. And so lambda plus lambda minus is equal to lambda. And so if we define A plus and A minus based on the eigenvector matrix, but using lambda plus and lambda minus instead of lambda, then when we add those two together, A plus added to A minus is just R times lambda plus lambda minus times R inverse, but that's R times lambda R inverse, so that's the original A. So you can view A as being split up as this combination A plus A minus, and one way to write this sort of wave propagation form of the Upwind method is that we use the A plus matrix times Qi minus 1, and the A minus matrix multiplying Qi plus 1 minus Qi. And it looks essentially exactly like the advection equation Upwind method, where we had U plus and U minus, but this allows it to generalize to any system, any linear system of equations. So you could, in practice, actually calculate these A plus and A minus and implement it this way, although, again, it's typically more efficient to think about just splitting up each jump into eigenvectors and then summing up the wave contributions, especially when we get into variable coefficient or nonlinear problems where the matrix is changing everywhere. So again, there's a couple of different ways that you can look at this Upwind method. You can either look at it as modifying the cell average by all of the waves coming in from the right boundary or the left boundary, or you can combine those into these matrices A plus or A minus times the intermediate state, or you can write it in terms of A plus and A minus times the jumps in Q. Yeah, in special cases, if all the eigenvalues are positive, then A plus is just A and A minus is 0, for example, and this would just reduce to what looks like a one-sided method based on looking at the correct direction for the sign of all the eigenvalues. Okay, so very briefly, let's just look at what happens when you apply this to acoustics. So acoustics is exactly the sort of picture here where we have two waves coming out of each Riemann problem. And so in each Riemann solution, we have one intermediate state between the values Qi and Qi minus 1, for example. And I've changed notation here a little bit. I'm using a star here instead of that Riemann symbol. But these Qi minus a half star would be the value along the interface Xi minus a half when we solve the Riemann problem between Qi minus 1 and Qi. And so the solution at the advanced time has three states. If we're looking at sort of the solution within a grid cell, there's sort of three segments here. One where it has the value that's the intermediate state coming from the left, one where it's the original Qin, and one where it's the intermediate state from the right. And so if you think of computing the new cell average Qin plus 1 just by averaging those three states, taking into account the length of each of those segments, which relates to how fast it's moving, the wave speed, the sound speed c times delta t shows how far each of those waves moves into the cell, then you can work out this expression for the cell average by just averaging those three values, which looks kind of messy, and it doesn't look at all like anything that would come out of a sort of finite difference approximation of the acoustics equations directly, but it's based on the idea of these waves and the eigenvalues and eigenvectors. So another way to write that again is a little more natural in terms of implementing it, and that extends better to more systems, is to think of it in terms of solving the Riemann problems, so that we decompose each jump in Q into these waves, which are proportional to eigenvectors, and then we can write the intermediate states in terms of those waves. And if you plug that in and do some manipulations, what you end up with is this expression at the bottom, where again we see that the cell average is updated by taking the previous cell average and adding in the two wave coming from the left boundary times the distance c delta t it's moving in, and the one wave coming from the right boundary times the distance minus c delta t that it's moving in, and dividing by the cell width delta x. So that's sort of the wave propagation form that's actually more natural for implementing it, I think, but that's equivalent to doing this averaging of the three states at the advanced time. That's the same thing, but then again, just reminding you what it looks like for a system of M equations, where we're just summing up over the left going or the right going waves coming from the left edge and the left going waves coming from the right edge. And this is, again, the picture that maybe helps keep it in your mind of how you would be updating a cell average in the case of three waves.